Hello from Pittsburgh. I'm Matthew, and I'm here to talk about composing and decomposing op-based CRDTs with semidirect products. And this is joint work with Heather Miller and Christopher Meiklejohn. To start off, I want to briefly recap op-based CRDTs. These are eventually consistent replicated data types where you have a group of replicas that maintain copies of some shared state, such as maybe an ad counter. Replicas can update their own copies of the shared state at any time without coordination. They then send messages describing these operations to other replicas, and these messages are assumed to be delivered in causal order. So because replicas can update their own copies of the state without coordination, you might end up with concurrent operations, which could then be delivered in different orders to different replicas. Thus, to ensure that they all end up in the same state, you require that concurrent operations commute. To accomplish this, you typically have to add some metadata to your state series messages. A simple example of an op-based CRDT is a counter, like what's illustrated here, where you have +1 operations to increment the counter. So here, this is easy because the +1 operations naturally commute, so you don't actually have to worry about concurrency. More complicated example is something like an add-win set, where add and remove operations don't naturally commute, so you have to do some form of conflict resolution. And this is true in general. If you want to design a CRDT for a new data type, you have to figure out what to do when there are commuting or non-commuting concurrent operations, and you have to prove that your new design is correct. This makes it hard to design CRDTs for new data types. For example, suppose you wanted to make an integer register CRDT, where the state is just an integer value, and where your allowed operations are add and multiplication. So looking at the sequential semantics, ignoring concurrency, you could have something like you start in state 1, multiply by 3, and then add 1. So the challenge is to make this into a CRDT so that you can have a group of replicas who might issue operations concurrently. So handling add operations alone are easy. They already commute with each other. And similarly for multiplication operations alone. But if you have concurrent add and multiplication operations, they don't actually commute. So let's say we have two replicas A and B that start in state 1, and then replica A says to multiply by 3, while at the same time, without communicating, replica B says to add 2. Okay, now they exchange these operations, and if they just apply them directly, then replica A will end up in state 4, while B will end up in state 6, which is not what we want. So we need some form of conflict resolution that handles these concurrent and add multiple operations. So the highlights of our work is that we present a general CRDT construction technique, the semidirect product, which gives a CRDT for this integer register example and many others. And what it is a construction that combines two op-based CRDTs acting on the same state space. It makes a new CRDT with operations of both of the input CRDTs. And it resolves conflicts between their non-commuting operations in a uniform way. An example of this combination is that we can take a set that only supports add operations, which is pretty easy to make into a CRDT, and a set that only supports remove operations, and we can combine them into a set CRDT that allows both adds and removes. A special case of combining two CRDTs in this way is adding operations to an existing CRDT. Using our semidirect product, we construct both old and new CRDTs, by which I mean we both decompose existing CRDTs as semidirect products of simpler CRDTs, and we build CRDTs for new data types. So an old example is we show how to add an observed reset operation to a CRDT using a semidirect product. And this CRDT is used in the React map to handle removal of values. For a new example, we give the integer register that I described on the previous slide. And that's what I'm going to talk about in this talk. If you want to see the general construction, you'll have to look at the paper. Okay, so this is our goal. I'm going to make the integer register. And the solution I described will be the semidirect product of an add-only register with a mult-only register. So recall the bad situation from before. We have concurrent adds and mults, and we just apply them naively. We end up in different states. We have to decide what to do in this situation. So for our first attempt, let us dictate that when replicas receive concurrent add and mult operations, they'll internally reorder them so that they apply the adds before the mults. So in this example, when replica B receives the operation mult3 from A, they say, okay, this mult and add are concurrent, but I've done the add first like I should, so I'll just apply the mult3 naturally and get 6. And when replica A receives the add operation from B, they say, whoops, I did these in the wrong order. I need to undo my mult, reorder the operations to be add then mult, and then apply that to my initial state of 1. And so A also ends up in state 6. Now you might be thinking, this seems too easy and maybe it's not well defined in general. And you're right, we can give an example where there's actually no ordering that works. So here we have two replicas A and B that both start in state 1. Replica A says to multiply by 2 and then add 1. Well, concurrently, so without communicating, B says to multiply by 3 and then add 4. Okay, now they exchange these messages. So each replica has copies of all 4 messages. They have to decide what to do. So what we said was that they should reorder their operations so that adds come before concurrent multiplies. So here, mult 2 and add 4 are concurrent, so add you go first. Add 1 and mult 3 are concurrent, so add you go first. And we would also like for causally ordered operations to stay in order. So the operations issued by A and B in order should still be issued in that order. But you can see now we've made a loop. There's no way to actually reorder these operations that respects the 2 rules we've given here. Okay, so that doesn't work. Okay, so we're back to square 1. We have to deal with concurrent adds and multiplies. For our second attempt, let's observe that if a replica receives add and mult operations in the wrong order, so they receive the mult before the add, they can still get the right result if they transform the add by the mult. So here, we still have that B is doing things in the right order, so they can just apply the mult 3 operation literally. But now A, when they receive this add 1 operation from replica B, they say, uh-oh, this is concurrent to the mult 3 operation that I already applied. So that's the wrong order of mult before add. I can fix this by just adding 3 times 1 instead of adding 1, okay? Now both replicas end up in state 6. And the reason this works is just a distributive law. So what replica B does is they start in state 1, they add 1, and then they multiply by 3, whereas replica A starts in state 1, multiplies by 3, and then adds this transform value 3 times 1. So a more complicated example is the one I showed you as a counterexample to attempt 1. This is the one that makes the cycle. So now when replica A receives the mult 3 operation from B, they just apply it normally. And then when they receive this add 4 operation from B, they say, okay, this is concurrent to the mult 2 operation that I already applied to my state. So instead of adding 4 directly, I'm going to transform it by multiplying it by 2. And so they end up in state 17. Now replica B, when they receive this mult 2 operation from A, they apply it normally. And then when they receive the add 1, they say, okay, this add 1 is concurrent to my mult 3 operation, which I applied first, contrary to the desired order of add before mult. So to fix this, I'm going to transform the add by multiplying it by 3. And you can see that both replicas end up in state 17. In general, the way our CRDT works is when you receive an add operation, instead of applying it directly, you first transform it by all the concurrent mult operations you've already received. So add m becomes add of n1 times n2, etc. times m, where mult n1 through mult nk are all of the mult operations the replica has previously received that are concurrent to the newly received add operation. And the fact that this works in general isn't too hard to prove. I'm not going to give you the proof here, but it's basically just a distributive law. Formally, to make this into a CRDT, you would track the concurrency status of messages by attaching vector clocks to each operation. And then when you receive a mult operation, you'll store it in a history together with its timestamp as part of the CRDT metadata. Okay, so that's the integer register supporting add and mult operations. Now for an example of an existing CRDT that can be written as a semidirect product, I'll discuss the observed reset CRDT. So in the react map, which is a CRDT representing a map from keys to CRDT values, when you remove a key, the map applies an observed reset operation to its value, which restores the value to its initial state. And this only affects causally prior operations. So if someone concurrently changes the value at that key, then it'll resurrect the key with a value of the initial state affected by the concurrent operation. Okay. So if we ignore the map aspect of this, you can see that each value is a CRDT, which has the original value CRDT operations plus this observed reset operation. We can think of that as a new observed reset CRDT. So for our semidirect product decomposition, we decompose this CRDT with reset operation as a semidirect product of 2 simpler CRDTs, the original CRDT without a reset operation, and a CRDT operation, or a CRDT that has the reset operations only. Okay. So to do this, to make our semidirect product, we have to choose which CRDT's operations should go first in the case of concurrency, like how we had to choose that add should go before mult in the previous example. So what we do is we choose the resets, and this means that if you have a reset operation concurrent to a non-reset operation, the reset will go first, and so the normal operation will go later and not get destroyed by the reset. This gives us the absorbed reset semantics. Having made this choice of which operations to go first, the rest of the construction is pretty easy. The semidirect product does most of the design work. And there's a lot of further examples in the paper, which I encourage you to check out if you're interested. And that's all I have to say for today. There's a lot more in the paper, especially the archive version, which is cited in the proceedings version. And with that, it's time for questions.